Okay, welcome back. So, two extremely important theorems in this next section, Rolle's theorem and the mean value theorem. Okay, these theorems will come up again and again, I guess, proofs. If you took like an advanced calc class, I presume you would have a better understanding of these things. Seems like we don't really use them all that much. I mean, they come up in proofs, so like I just said. But anyways, the math geniuses from Mount Math Olympus seem to think that these things are important. So we're going to go with them rather than my humble opinions on math. So the first theorem is Rolle's theorem. Okay. And if nothing else, you appreciate the sort of chain of logic that's being put into effect here to obtain this theorem. It's theorem 4.3 in the book. Let's write it out and see what it says. Let f be continuous on a closed interval. Okay. And of course, if it's continuous on a closed interval, that means we could use the extreme value theorem to say it has both a max and a min. Okay, well, that's good. So anyways, f's continuous on this closed interval, and then it's differentiable on an open interval. I butchered that word. On an open interval from A to B. Then it goes on to say if the height at the endpoints, if f of A and f of B are the same, then there is at least one number C such that f prime of C is equal to 0. Okay. Okay, so that's the theorem. Generally, as a new student, how I would think of this is visually. Basically, you have some sort of function that is the same at the endpoints, has the same height, you know. And then what this theorem is saying is that somewhere in between these two endpoints, there's going to be a horizontal tangent line, right? So there's going to be at least one point. In this example, I have two, obviously. But the Rolle's theorem says there's at least one C value such that the slope at that point, the slope of the tangent line at that point is equal to 0. Okay. Okay. So visually is how I would begin to appreciate this thing. Let's take a look at the actual proof. Okay. And there's going to be two cases. So the first case is where the function is constant on the interval. So case 1, we'll say f of x is equal to d, which is equal to f of a, which is equal to f of b, for all x on the interval. In that case, because what is this? It's just a horizontal line. You can pick any point, and that'll be true. Okay, so hence f prime of c will just equal 0. The derivative of a constant is just 0 for all c in this interval from A to B, which is what we're trying to show, right? We're trying to show and a constant function is continuous. Okay, it's also differentiable on these intervals. Also, f of a is equal to f of b. They're both equal to d. And then we noted the derivative f prime of c is equal to 0 for all c in this interval. So therefore, we have this conclusion. Okay? So given a bunch of suppositions, we need to show via calculus and algebra that this conclusion, there exists one C such that f prime of C equals 0 follows. Okay, so that's case one. Case two, then, we're presuming that f is not equal to some value for all of its interval. And in that case, f of x is going to have to be higher than its endpoints or lower than its endpoints at some point. So we'll suppose the earlier case, suppose there exists some point, I think I would just call it x, in the interval from a to b, such that f of x is greater than whatever these endpoint values are, f of a, which equals f of b. And I don't know why we don't call this like x hat or something. Let's just give it a name, x hat. Suppose there exists an x hat such that in this interval from a to b, this f of x hat is greater than f of a and f of b. In other words, pictorially, if we have f of a and f of b right here and right here, I'm saying there exists some x hat in between such that f of that x hat is above f of a and f of b. Okay, and this has to be true because we're presuming that f of x is not constant. It could be the other case, but the other case would probably be very similar, right? If we suppose that f of x hat was less than f of a, which equals f of b. Okay, so what? Well, first off, f is going to have a max in this closed interval, right? And that's from the extreme value theorem. So first off, f of x has a max in the interval from a to b. And this is because of the extreme value theorem. So if you've forgotten, so long as the function is continuous on a closed interval, then it'll have a max and a min. In this case, because this guy is going above the f of a and f of b, I can presume that there's going to be a max that's not equal to its endpoints. Okay, so secondly then, the max is not at an endpoint. And that's because f of x hat already we know to be greater than f of a, which is equal to f of b. Okay, so there exists some c value in this interval. So thirdly, there then exists a c such that f of c is a max, and c is in the interval from a to b. Okay, and it's not equal to a, it's not equal to b. So this, by definition, means that this is a relative max. Okay, so when you have a max in an open interval, it means it's a relative max by definition. Okay, that being said, if this thing is a relative max, we got a theorem that says if f of c is a relative max, then x equals c is a critical number. Okay. the definition of critical numbers said that either f prime of c was equal to 0 or f prime of c is not defined. In this case, f prime, the derivative, must be defined because it says it's differentiable on the open interval from a to b. So it must be the case that f prime of c will equal 0. Okay. And that does it, right? That's kind of what we were trying to show. We're trying to show that there exists some c value in between a and b such that f prime of c equals 0. And that's kind of what we did via this chain of logic, right? So just going through the steps again, and usually in the book you won't see it listed out. This is a great way to read proofs as you go through it. You're just collecting facts, why is the fact true, and kind of seeing how they go point by point until you get a conclusion. Okay? Obviously, you never write a proof like this, but you want to have that skeleton kind of in mind. So anyways, we split it into two cases. The first case, the function is a constant. If the function is a constant, you take its derivative, it's automatically equal to 0. So the slope would be equal to 0 for all c in the interval. So the other case is where it's not constant. If it's not constant, then you can either pick out a value like this or pick out a value below such that f of that value will be greater than the endpoint values. Okay, then by the extreme value theorem, the function will either have a max or a min. We'll go with the max because we presume that this thing goes above the endpoints. Okay. The max is then not at an endpoint because of the way we presume that x is above f of a and f of b. By definition, then, it's a relative max because it's a max that occurs on an interval. And then we had a theorem that says if f of x is a relative, if f of c is a relative max or a relative min, then it's a critical number. So we said x equals c is a critical number. And then the definition of a critical number, f prime of c is equal to 0 or f prime of c is not defined. But we have the supposition that the thing is differentiable on this open interval. Therefore, f prime of c must be equal to 0. The only other case is f prime of c is undefined, but that's not true because of our supposition, right? So it's just, a lot of math later on, if you wanted to keep studying math, is like that. It's just pure thought and making arguments and logic and convincing people that what you think is true. Okay, so it's a lot. And remember going for a job interview and research, math research, and I was talking to the guy who was, thinking of hiring me. I didn't get hired, but he was thinking of hiring me, and he was talking about his daughter had the job before me, and she left the job to become a lawyer. So it's very related. Philosophy is mixed in there, and good stuff. Okay. So anyways, let's look at a couple of problems, and then we'll do the mean value theorem. Okay. So the first thing is you need to make sure that the criteria hold in order to do Rolle's theorem. So determine if Rolle's theorem can be applied, and if so, find the c where f prime of c is equal to 0. Okay, so for these problems, you need to show that the f is continuous. Secondly, you need to show, and continuous, what I mean, it has to be on a closed interval. And then you have to find, is f differentiable on this open interval? And if that's all true, then you can look for this c value such that f prime of c is equal to 0. Right? So it's kind of a three-step process here in these problems. So let's look at number 15. We have f of x equaling x squared minus 2x all over x plus 2 on the interval from -1 to 6. Okay. So is this thing continuous on a to b? So can you take its limit and just do a substitution? And that will be true everywhere except where the denominator is equal to 0. So first, note this thing's not continuous at -2. But everywhere else, it's good. It's just a ratio of polynomials, and those things are continuous everywhere except for that denominator is equal to 0, and I just found that. Okay, this thing is not in our interval of concern, so it doesn't matter. But it's continuous in the intervals, and that's all we care about. Okay, so that first part is kind of checked off. Secondly, is the thing differentiable on our open interval? Okay, so if you take a look at that derivative, and usually I just look at the derivative and see if the derivative works. Okay, so f prime of x low d high minus high d low all over the low squared. And clearly, the only problem with this guy is going to be at -2 again. So on this interval, it's going to be defined. So f is differentiable on our interval. Okay. All right. So thirdly, we want to find the c value. Okay. So I'm going to clean this up a little bit in order to make this happen. You can FOIL this thing out. I don't know if we can I factor something out? Not really. So let's clean it up. The derivative f prime of x is, all right, so 2x squared, first outer, minus 2x inner plus 4x minus 4 minus x squared plus 2x all over x plus 2 squared. And then that equals, let's see, 2x squared minus x squared is 1x squared. 2x plus 2x, 0. And then plus 4x minus 4 all over x plus 2 squared. Okay. We also need to make sure the endpoints are the same. So I guess we have 4 things I need to look for. 4, I need to make sure that f of a is equal to f of b. So let's get that out of the way as well. So not done yet. I'll need to figure out where f. Yeah. All right. So I sort of skipped this step. I need to come back and do it. So f of -1 is 1 plus 2 all over -1 plus 2. So that would be 3 all over 1, which is 3. F of 6 then is 36 minus 12 all over 8, which is 24 over 8, which is 3. So yeah, that part was fulfilled anyways. Getting back to step 3 then, I need to figure out where f prime of c is equal to 0. And that's guaranteed to exist somewhere because of what we've been doing, the Rolle's theorem. All the criteria are holding. So I just set this thing equal to 0. You could plug a c in there if you want. You're setting the derivative equal to 0. This equal to 0. And solving. So c squared plus 4c minus 4 all over c plus 2 squared equals 0. The cross multiply or just set the numerator equal to 0. Okay. And then solve that thing. Looks like we don't need a quadratic formula, unfortunately. So c equals -4 plus or minus square root of b squared minus 4 times a times c all over 2 times a. Okay, so this would be -4, running off the page there, -4 plus or minus 16 plus 16, so square root 32. So 2, excuse me, that'd be 4 root 2 all over 2. And then you can simplify, and we get -2 plus or minus 2 root 2. And we want the one that's in our interval. There's 2 answers here. We need to make sure it's in the interval from -1 to 6. And the only one that'll work is the plus version. So if you check it on your calculator, it's obvious. I already did it though. So hence our C value, in this case, -2 plus 2 root 2. Let's look at number 19. So we have f of x is tan x, and we're on the interval from 0 to pi. All right. So you got to go through and make sure it's continuous on the interval 0 to pi. No, it's not, right? So remember, tan of x is equal to sine of x over cosine x. And then if you plugged in anything that made cosine 0, for instance, on our unit circle from 0 to pi, at pi over 2, cosine is 0. So right here, and that's in this interval. So no, it's not continuous, and therefore Rolle's theorem can't be applied to find this value. In fact, if you look at the thing on that interval, right, so going from negative pi over 2 to pi over 2, it looks like this. And then again, from pi over 2 to 3 pi over 2, it looks like this. Right? So from 0 to pi, there's a ton of business going on. There's things going to infinity. There's things going to negative infinity. So for any big value you give me, I can find one that exceeds it. Any small value you give me, I can find one that exceeds that. There is no min or max here. Even if you try to do some restriction, well, if you did a restriction like from 0 to pi over 2, then it would have a min. Okay? But anyways, you know, what are we looking for? We're looking for the places where the derivative is horizontal, and there just isn't one on the tan function. There are none. There are no places where f prime of c is going to be equal to 0. So yeah, I mean, this thing is just not continuous. Rolle's theorem won't apply, and we can't even kind of look at the graph and find a place where it would work. Okay, so there's that one. Okay, so after you play around a little bit with Rolle's theorem, you want to take that up a notch and walk into the mean value theorem, which is kind of what we need. Rolle's theorem is just a means to an end. Okay? The mean value theorem is what we're really after. And again, let's go ahead and write out the definition, and then I'll give you a graphical version, and then we'll go through the proof. Okay? So if f is continuous on the closed interval from a to b, and then differentiable on the open interval. Let's just say open interval from a to b. Then there exists a value c in that interval such that the following craziness is true. And what is that craziness? The craziness is that f prime of c equals f of b minus f of a all over b minus a. Right? Okay, so one takeaway here, the criteria, this continuity and differentiability, is very similar to Rolle's theorem. So we're going to end up using Rolle's theorem here in order to prove that this statement is true. So what does this statement say visually? Visually, what it's saying is that if you have 2 points, f of a and f of b now, such that they're not the same, so unlike Rolle's theorem, you can have values one above, one below, then there will exist some value in between here such that the derivative at that value will have the same value as the secant line through these two endpoints here. Okay, so the slope here is equal to f prime of c. The slope of this line is, well, f of b, it's this thing. This is just a slope formula, right? F of b minus f of a all over b minus a. Okay, and the way intuitively I think of it is just if you were to be able to rotate this figure over like this, it's basically just Rolle's theorem. Okay? And I think, I don't know. All right, so let's look at the proof of why this is true. And again, it's the idea that we can use Rolle's theorem. One thing they like to do sometimes is create another equation and then apply a previous theorem to that to get this new resulting statement. So let me make this picture a little bit more clear, kind of zoom in on it. So we have A, B, then we have some sort of graph over here. So we'll call this graph f of x, and this point is f of a, and this point is f of b. Okay? So the points on my graph are, this guy is b comma f of b. This guy right here is a comma f of a. Oops, sorry, that's off the page. And what we're going to do is create a new function and apply Rolle's theorem to it. Okay? So the new function is going to be f of x, and then I guess minus the secant line from here to here. So I need to create an equation for the secant line from here to here. Right, so we're going to call that secant line y. Right, so the proof then, note the secant line y is as follows. And to get that secant line, you use point slope formula, right? So you use y minus y1 equals m times x minus x1 on these 2 points here. Okay, so the secant line y will be the slope of the secant line, which is f of b minus y2 minus y1 all over x2 minus x1 okay, times x minus a, and then from the other side you're adding in the plus f of a. Okay, so it would be y2 minus this would be our y1, x minus x1. So if you remember your formula for point slope, y minus y1 is m times x minus x1. I'm just plugging these 2 points into this formula to get this thing. All right, so now I'm going to create a new equation based off of this. Consider then this new equation, which I'm going to call g of x, which will equal f of x minus this guy right here, minus y. Okay. So in that case, what will this guy look like? It'll be equal to f of x minus this business right here, this secant line business. So minus f of b minus f of a all over b minus a times x minus a, and then minus f of a. So that'll be my g of x. Okay, so some things to note about g of x. And the things to note are basically we're just going to go through the criteria for Rolle's theorem. Okay, so for Rolle's theorem, we want the endpoints to have the same value. So note, firstly, g of a equals g of b. So g of a, if you plug a into this formula, what do you get? Well, you get f of a minus, if I plugged a into here, that would be 0. So this whole thing is going to be a big 0. And then minus f of a. And of course, that equals 0. Okay. For g of b, a little bit different. Here, that'll be plugging b into here for x. I got f of b. And then minus f of b minus f of a all over b minus a. And then I'm plugging in b for x. Okay, so this will be times b minus a. and then minus f of a. Okay. Right here, these b minus a's divide out. You got f of b minus f of b, and then if I distribute the negative, plus f of a, and then minus f of a. And of course, that will just be 0 again. So the endpoints are the same for this function. What else did we need? We need g of x to be continuous on the closed interval and differentiable on the open interval. Okay, so we note f of x is continuous and differentiable on the appropriate intervals. So this thing is just a difference between f of x and a line. And if you remember kind of how operations worked with continuous functions, if you have two functions that are continuous and you add them together, they're still continuous. And in this case, because we're just tacking on the equation of a line, its derivative is continuous everywhere. So it'll turn out that that extra bit is not going to affect the differentiability of this part of it. Okay, so note f of x and y are both going to be continuous and differentiable in the appropriate places. So f of x and y are continuous on the closed interval from a to b and differentiable on the open interval from a to b. Okay. Because we've assumed that f of x is going to be that way, and then because the y is just the equation of a secant line, it's going to behave that way. It'll be continuous and differentiable everywhere. Okay, so the sum of these two will be continuous and differentiable everywhere. Or in this case, the difference. Will also hold these characteristics. Okay, so what we have then are the criteria for Rolle's theorem holding. And so therefore, by Rolle's theorem, there exists a value c in this interval from a to b such that f prime of c is equal to 0. Okay? In particular, our case, we're using this function g. So instead of saying f prime of c, let's say g prime of c is equal to 0. Let's see what g prime of c just exactly is, right? So if we took the derivative of this thing, g prime of x, that would equal f prime of x minus the derivative of this line, right? And the derivative of the line is just its slope, so it's f prime of x minus f of b minus f of a all over b minus a. So when we say g prime of c equals 0, we can rewrite that, noting that g prime of c is actually equal to, well, f prime of c minus f of b minus f of a all over b minus a. Okay, and then this thing's equal to 0. So if I just zoom in on this part of my chain of equations, well, I can solve this for f prime of c, and I'll have what I'm after. Okay, so here then, f prime of c will be equal to f of b minus f of a all over b minus a. Okay, so it's a long journey getting there to the mean value theorem, but we made it. All right, let's apply this thing and see what kind of homework problems you're looking at. But this is a tool you can use now from this point on to prove things, if you're so inclined. Anyways, we have f of x equals x cubed plus 2x on the interval from -1 to 1. So first, we need the criteria fulfilled. We need it to be continuous and differentiable on the appropriate intervals. So first off, is it continuous on the interval from -1 to 1? And certainly, any polynomial you can do a substitution limit on. You remember, continuity is kind of like, does the limit behave via a substitution type limit? So can I find the limit as x approaches c of the function x cubed plus 2x for any c value, right? And that's always, yeah, that's going to be the case. We just plug c in there. And when you could do that, the thing's considered continuous, okay? So yes, polynomials we know hopefully are continuous everywhere, but if you didn't know that, you could finagle the limit definition of for continuity to make it happen. Secondly, then, is the thing differentiable on this interval? And certainly, yes, it will be. And it only needs to be on the open interval from -1 to 1. It doesn't need to be on the closed interval. Yes, we can look at the derivative. It's right here. Look, it's 3x squared plus 2. It'll have a value for the slope of the tangent line at any point on that curve. So yes, it's differentiable. So hence we can apply the mean value theorem and find a c value in between these 2 points such that the slope of the tangent line at that point is equal to the slope of the secant line between -1 and 1. Okay, so let's make that happen. I need to find a c value such that f prime of c is equal to f of 1 minus f of -1 all over 1 minus -1. Okay, so the derivative of this thing is, what, I didn't find the derivative? Yeah, it's right here. Okay, so I'm plugging c into that, so 3c squared plus 2. And then I'm plugging 1 into the original function, so I have 1 cubed, which is 1, plus 2, minus -1 cubed, which is -1, minus 2. And that's all over 1 plus 1 is 2. Okay. That'll be 3c squared plus 2, equaling 1 plus 2 is 3, minus -3. So it would be 3 minus -3, or 3 plus 3. Is 6 over 2. 6 over 2 is 3. Solve this. 3c squared is 1. So c squared is 1/3. So c is plus or minus square root 1/3. And both of those are in this interval. So we actually had 2 c values this time such that this thing occurs. The slope of the secant line is equal to the slope of some point inside the interval. I don't know, what could possibly be of interest for this? What could we use this for? Well, if you look at a really super duper small interval, like from here to here, you can kind of presume that you can, I don't know, get a slope value. I don't know what it is. It seems almost like it's a matter of an approximation. You can kind of always replace the slope from this point to this point with the derivative. Okay? And that turns out to be kind of important later on because there's a connection between distance between 2 points and derivative slopes. The place I'm thinking of is the distance formula. If you have x 2 minus x1 squared plus y2 minus y1 squared, and you factor out x2 minus x1. So this is distance as it sits, but if you factor out the x2 minus x1, you get a flavor of a slope. You get y2 minus y1 all over x2 minus x1 squared, and this guy right here is slope. Okay, so on super duper small intervals, you can approximate that slope using the mean value theorem. And so there's weird connections all over the place in math. Let's look at one more, and then we'll call it probably quits. So 47, we have the function f of x equals sine x. And excuse me, we're worried about the interval from 0 to pi. So first off, is it continuous? And yeah, sine function is really well behaved. You can always do a substitution limit. So yes, there's no vertical asymptotes or anything crazy. Is it differentiable on the open interval from 0 to pi? And then, yeah, of course, again, yes, the derivative is just the cosine function, which is continuous everywhere. What else? That's all we need for this to work. Then we could say, let's find where f prime of c is equal to f of pi minus f of 0 all over pi minus 0. Okay, so the derivative of sine is cosine. F prime of x is equal to cosine of x. So f prime of c is cosine of c. On the other side, f of pi, sine of pi is just 0, minus f of 0, which is 0, all over pi. So we're looking at solving the trigonometric equation cosine of c is 0 on the interval from 0 to pi. And that, of course, happens when c is equal to pi over 2. Okay. Okay. Yeah, so a lot of technical business, but the math people would be terrified if I was not going through the proofs and everything for you. So I had to include those. Okay, that's good enough. I'll say bye.